Hi, we're back, and I'm really excited about this video. This video is going to be talking about Newton's method for using derivatives to find x-intercepts, or as we call them in algebra, 0 points. So in other words, when a function f of x crosses the x-axis, that's a 0. And so we're solving for those intercepts there when y equals 0, using calculus that we know to this point. And this is section 4.7. The reason why I'm so excited for it is because I haven't taken this class in a long time, and although I've tutored it, I never actually took the time to sit down and prove Newton's method to myself. And so I had a blast doing that for about the last 30 minutes, and I'd like to share it with you. And knowing that the first time I went through this class, I had no idea what this was. I knew it was an estimation method. It's by no means analytical, it's numerical, it's all estimation. And how accurate your estimate is depends on how much cold, hard calculation you're willing to do until you get exhausted. So the idea of this is, let's say that we have this blue curve as a function of x, okay? So the first thing we do in Newton's method is we pick a point, and we call that point x1. So I picked a point x1, okay? And then I went up to the ordered pair on f of x. So when I plug in x1 to f of x, I get f of x1, and we'll just call that y1, okay? So, in other words, I pick an x, I get an output point. The next step is we're going to find the tangent line. We're going to find the tangent line from that point, and we're going to follow the tangent line at that exact point to the point at which that linear line crosses the x-axis again. And once it does, we're going to mark that point and call it x2. Now, once we have x2, we're going to follow that and plug it into f of x. So when you plug in x2 to f of x, you get x2 and f of x2 as the ordered pair. And I'm just calling f of x2 y2. So this is the ordered pair x2 and y2. Then once again, we use the derivative to find the tangent line to that point on the graph. And then we follow it to where it intersects the x-axis again, and we call that x3, and that's where I decided to stop drawing it, because it's infinite and it's recursive, and so I could just keep drawing them, and although I would never get to the true point where this graph crosses the x-axis, the theory is I will keep getting closer every iteration. There are a few exceptions to this. For example, what if I picked 0 here? So what if I picked x equals 0? If I picked x equals 0 as my x1, and I went up to f of x1, I would notice that the tangent line never crosses the x-axis. So in some cases, Newton's method isn't going to work. But if you're anywhere, in this range from about there to there, you're going to end up finding a pretty good approximation after a few iterations. If you find that you're getting nowhere with the method, that probably means that you are picking a point where the tangent line has a slope of 0, and so it never crosses the x-axis. Alright, so now to the derivation. So the concept here is that, so let's start here. I pick an x1, I go up to my ordered pair x1, y1, and I'm curious about the slope at that point. Well, we know that the derivative will give us the slope of any point on a graph f of x when we plug in that x value. And so with that logic, if I take f prime of x, or the derivative of x, and I plug in x1, I will in fact get my first slope. So I've got this slope now. Now I don't know where it is, but I know it's slope. I just don't know quite where to peg it yet. And so the important part about this next part is we're going to say that y equals mx plus b. Once again, we're dealing with lines, so this will always come in handy. So our slope is going to be m1, and we know x and y; those are variables, but we're looking for b. Well, we know what m1 is, so m1 y equals the derivative of f of x plugging in x1, x plus b, so we're doing that slope substitution. And we can solve for b by plugging in the ordered pair points x1, or x1, y1. So when we have y1, we also have x1. So you see now I can solve for b in terms of x1, y1, and my first slope. So I will now solve for b. b is equal to y1 minus f prime x1 times x1. Well, now I can go back to my original function here, and I can plug in b. So now I get y equals f prime of x1 times x plus b, which is y1, minus f prime x1 times x1. And it's important to realize that when we solve in terms of y1 and x1, those are real numbers. These y and x variables are variables. So then at this point, what we can do is we can, well, here's the thing we're looking for, right, is we're curious about when this line crosses the y equals 0 line. So this is the y equals 0 line. So how about we set our variable y equal to 0 and solve for x? So we set y equal to 0, and we still have f prime of x1 times x plus y1 minus f prime x1, x1. And so now we're curious about where x will be, right? Well, we already kind of labeled that, right? We decided where this line crosses the x-axis. We're going to call that x2. And we want to solve for x here. It turns out x here is actually x2. So it's x2 there because that's the x that we're solving for when it intersects the y equals 0 line. And so now let's get x2 all on its own, because that's what we're looking for. We want to know where x2 is. And so we can subtract f prime of x1 times x2 onto the left side of the equation, and leave the right side of the equation as y1 minus f prime x1 times x1. Alright, so we've gotten to this point. I'm going to move up here. And why don't we divide this negative f prime of x1? That way we get x2 alone. So x2 is equal to, now we have y1 divided by f prime of x1. And by the way, that's a minus f prime of x1. And then we're subtracting f prime of x1 times x1 divided by negative f prime of x1. So we just divided this negative f prime of x1 over here, and what you'll find is that right here, these two cancel. A negative and a negative makes a positive. So we've simplified it to x2 equals y1, or I'm sorry, this is negative because of the negative f prime of x1. So now we have negative y1 over f prime of x1, and we're actually adding x1 to it. Okay, so these two canceled, minus and a minus gives us a positive, and there's just one more step to get it to look like the method, the equation up here. This is the equation that you're going to be using. I just wanted to prove it to you and kind of show you conceptually what's going on. That's why I'm doing this. So, at this point, let's flip-flop these. So x2 equals x1. So I'm just moving this term here and that term there. Minus y1 over f prime of x1. Well, you know what we know about y1, right? y1 is the value we get out when we plug in x1 to f of x. So we could replace y1 with f of x1, right? Because at x1 we plug it in, we get f of x1, and we called that y1. So instead of calling it y1, let's call it f of x1. And at this point we find that to solve for x2, x2 is going to equal x1 minus f of x1 divided by f prime of x1. And that's very similar to what we have up here. The only difference here is that we write it in what's called an n style. So in other words, this works for any number, not just 1 and 2. So x2 is always 1 larger than x1. So we'll write that as xn plus 1 to indicate that it's always larger by 1 than x to the n. So x to the n plus 1 equals x to the n minus f of x to the n divided by f prime of x to the n. And as you can see, that's the exact same formula we have up here. I hope this was useful. Like I said, this always bothered me. Estimation methods were always something that I didn't appreciate. Hopefully this will help you to appreciate the method, even though it's very tedious and mundane. I hope this helped, and I'll see you next video.